Welcome to the deep dive. We got a bunch of great questions from you about garbage collection in programming. Seems like many of you want to get a better handle on this core concept.
Yeah, it's fundamental stuff.
Exactly. So, our mission today, unpack those questions. We're going to pull out the key ideas about this automatic memory management, what it is, why it matters for software, and maybe touch on some of the complexities without getting totally lost in the weeds.
Sounds good. Where should we start?
Let's jump right in. What is garbage collection, basically?
Well, simply put, it's an automatic process. The programming language itself finds memory that your program isn't using anymore
And cleans it up.
and reclaims it, yes.
Okay.
Frees it up. Think of it like an automatic janitor for your program's memory.
Okay, an automatic janitor. I like that. So why is that necessary? Why the automatic part?
Well, the main reason is to prevent memory leaks.
Right, I've heard of those. Nasty things.
They really are. If you have memory that the program allocated but isn't using and it never gets released, it just builds up.
And then crash. We're just slow way down.
Both can happen. Garbage collection stops that by doing the cleanup automatically. It's quite different from manual memory management.
Like in C or C++ proof,
Yeah,
where you have to remember to delete things.
exactly. With manual management, the programmer has to explicitly say, okay, allocate this memory, and later, okay, I'm done, deallocate it.
Which sounds like a recipe for mistakes.
It can be, yes, very error-prone. Forgetting to free memory leads to leaks. Freeing it too early leads to other bugs. GC helps avoid that whole class of problems.
Okay, that makes sense. But how does it know it's garbage? It can't just guess.
No, it doesn't guess. The key idea is something called reachability.
Reachability.
Yeah. The garbage collector, or GC, essentially looks at all the memory objects your program has created. Then it figures out which ones the program can still reach or access.
How? Like following pointers or references.
Precisely. It starts from known roots, like variables currently in use on the call stack, or global variables, and follows all the references. Any object it can find by following these paths is considered live,
And anything it can't find.
is unreachable, garbage, ready to be collected. If there's no active path leading to a piece of data, the program can't use it, so it's safe to reclaim that memory.
Okay, that concept makes sense. Are there like different strategies for doing the searching and reclaiming?
Oh, absolutely. There are quite a few algorithms. Two common ones you hear about are mark and sweep.
Mark and sweep.
Yeah. First, it marks all the reachable objects, the live ones. Then, in the sweep phase, it goes through all the memory and reclaims everything that wasn't marked.
Okay, and the other one?
Another popular approach is generational garbage collection. This one works on an observation, or a hypothesis, really,
Which is?
that most objects die young. New objects created in a program often become unreachable very quickly. Older objects tend to stick around longer.
Ah, okay, so it treats objects differently based on age.
Kind of, yeah. It divides memory into generations, usually a young generation and an old one. It collects garbage much more frequently in the young generation, where most garbage is expected. It's often more efficient.
Interesting trade-offs. Now, I've heard people complain about GC causing pauses, these stop the world events. What's the deal there?
Right. That's one of the main drawbacks, potentially. A stop-the-world event is exactly what it sounds like. The garbage collector temporarily halts the entire program's execution.
Stops everything.
Everything. While it does its work finding garbage, reclaiming memory, maybe reorganizing things.
How long are these pauses?
It varies hugely. Depends on the GC algorithm, the system, how much garbage there is. They can be very short, milliseconds, but sometimes longer.
And that can affect performance, right?
Mm.
Especially if you need smooth responsiveness.
Definitely. If you're building, say, a real-time system or a game, even short pauses can be noticeable or problematic. That's a big consideration.
So it really is a trade-off then. You get the safety and convenience of automatic cleanup.
Which is huge for developer productivity and preventing bugs.
But the cost is potential performance overhead in those pauses.
Exactly. Languages like Java, Python, C#, JavaScript, they rely heavily on GC. But their specific implementations and how they manage these trade-offs can differ quite a bit.
How does this compare directly to something like C++O, where you're managing it yourself, beyond just being easier?
Well, with manual management, if you're very careful and skilled, you can potentially achieve higher performance because you have direct control. You decide exactly when memory is allocated and freed.
But the risk is much higher.
Much higher. You spend more time debugging memory issues. GC trades some of that potential peak performance and control for safety and simplicity.
Can we as programmers help the garbage collector out? Write code that makes its job easier,
Yes, you can. Writing GC-friendly code is a thing. It often means being mindful of object creation, don't create tons of temporary objects unnecessarily, and also manage object lifetimes. If you have a reference to a big data structure you no longer need, explicitly set that reference to null or let it go out of scope. That makes it clearly unreachable sooner.
So basically, don't hang on to things you don't need.
Pretty much. Help the GC figure out faster what's truly garbage.
And you mentioned real-time systems earlier. Is GC just generally a bad fit there because of the pauses?
It can be very challenging. Those stop-the-world pauses are often unacceptable where you have strict deadlines. Some real-time systems use specialized GCs with very predictable pause times, or they avoid GC altogether and rely on careful manual management or different memory strategies.
Right. Okay. So boiling it down, garbage collection is this vital background task. It automates memory cleanup, saves developers from a lot of headaches and bugs.
Definitely saves headaches.
But it's not magic. It has performance implications, those potential pauses we need to be aware of.
Precisely. It's a fundamental part of many modern languages,
Yeah.
enabling us to build complex software more reliably than we otherwise could.
Yeah, it really makes you think, though. As software gets ever more complex, running everywhere from tiny devices to huge cloud systems, how will these GC techniques need to adapt and evolve?
That's the million-dollar question, isn't it? It's an ongoing area of research and innovation. Definitely something to keep an eye on.
Absolutely. Well, thanks. This has been a really helpful deep dive.
My pleasure.